Thank you, Chairman. I hope you can hear me all. I think I will go back a little bit to my technologies. I think there are a lot of people here who would like to bring these technologies and make a market out of that and earn money of it. So what I will talk today is about how synchronous condensers can participate in this environment of TSOs and DSOs which face problems in their grids. Now, that you see me already, so I don't need to have the slide. So I will focus a little bit, what is a synchronous condenser, why we need them, when we need them, where, and yeah, what it is. What is also decentralization means to that, and why decentralized generation will also reflect to decentralized ancillary services requirements. I will speak about synchronous condensers as a smart grid device, and then speak a few words about high inertia solutions. Now, when you look on the traditional grids, we are facing that our new distributed energy resources are coming in, renewables are coming in, all of those, or most of those are power generation devices which are non-synchronous. That means in reality, they are limiting the short circuit power in the grids, they are limiting the short circuit power contribution, they are limiting the inertia, they are limiting the phase angle stability between the grid areas. So they're creating a kind of headache which we have to face and which we have to deal with, because otherwise we jeopardize our stabilities in the TSOs as well as in the DSOs. So when it comes to a different type of implications, you can say that generation companies, the existing ones, they have problems with too big frequency variations. The rate of change of frequency make them that their power generation plants may drip off because of any kind of fault they will have on the grid. You may also see the transmission system operator, we have a problem that their relay protection settings are not anymore working because there is no short circuit power enough to drive the fault currents. They will also have the problems that there are so many power electronics connected that this power electronics is depending on a phase angle stability. That means a level of short circuit power which is there in the grid. If this is reduced too much, also the stability of the power electronics are not there. This will influence the HVDC links, this will influence the power electronics in our storage, in our converters, in wind and solar farms. On the distribution grid, we have the problem that during normal operation, of course, they will not get the short circuit support anymore from the transmission grid, and they face a problem that if there are more and more distribution energy resources are connected to these grids, during daytime when there is a lot of consumption, the short circuit power increase. And during nighttime, when nobody needs energy, but we still need the energy, the short circuit power will decrease to so low level that the voltage dips there will create big problems to our customers. And also the power quality issues will increase because there is no fault level which is holding back the power quality problems like harmonics, like negative sequence currents. And of course, who is then suffering? Well, it's the industry with these voltage dips caused by these faults which are not anymore helped by the short circuit power in the grid, where you will get deeper voltage dips which is influencing their frequency drives. Production will drip off, which costs a lot of money for them. And of course also then the final end client where we will suffer in our homes based on bad power quality. So there was a national grid did a kind of study which type of issues they are the big problems for them. And of course, as a national grid company, the TSO, they are speaking about frequency issues at once, and that the rate of change of frequency is the big issue for them. But there is also the problem that in some of the countries, they are decommissioning nuclear power resources, which means an additional reduction on inertia in their grids. So that means also this will be a high impact on some of the markets where we will lose inertia from our conventional power plants we have. So when do we need somebody who help us in the support of short circuit power, in the help of inertia, in the help of phase angle stability? Well, already today, transmission system operators are working with projects so that they can do it now. In Scotland, National Grid has developed a project called Pathfinder for Stability, where they have to install about 6,000 MVA short circuit power contribution to the grid to keep the system running in the future. The next will be in Wales. We have in Sweden, they are discussing the fast frequency response and support in the grid because we will decommission our nuclear power plants. In the Baltic countries, they will disconnect from the Russian grid, which is today the source for inertia for them. How shall they survive if there is no inertia and short circuit power contribution in the grid? In Scottish Power, we did for about 2 years a project which we called Phoenix. It's a combination between a synchronous condenser and a STATCOM solution. This was an innovation project which is today very much discussed, especially in UK, as one of the solutions which could help and secure this type of lack of inertia and short circuit power contribution, and combine that with the MVRs, which anyhow is already a kind of decentralized requirements to regulate the voltage. So where do we need it? Well, we need these supports, these condensers, or synchronous condensers, near the renewable power plants, where they could use this type of strengthening the grid to be able to deliver more of their active power to the grid, as those normally are connected in the remote areas, where normally the short circuit power is very, very low. We will see that in the transmission and distribution grid, as well as in the industrial plants, where they are already suffering from this big voltage variation caused by the non-existing short circuit power level. So what is a synchronous condenser? Well, in reality, it's a rotating machine, which is not a motor because there is no load. It's not a generator because there is no turbine. But once we are connecting the synchronous machine to the grid, we are providing, you can say, an insurance, like a short circuit current or fault support, inertia, and MVRs for voltage regulation, and phase angle stability for your grids, for your converters. And of course, beside that, we can also deliver the MVRs for voltage regulation. So we have then a little pony motor starting up the machine, connecting the machine then when we are up in speed, in the synchronous speed, to the grid, and then synchronize it, and then it's there, like an insurance. And if something happens, and it will provide you the right short circuit power and the right inertia required without any electronic device. That's smart grid. If you want to control then the voltage, then you can, of course, we can do that. And then we can do that with the conventional ways in controlling the voltage. With set points from you, or with requirements as coming from the wind farm controller or a solar farm controller. Now, I want to show you a little bit how decentralization is influencing. Now, I took an example not from the European transmission system operator or a DSO. I chose it from somewhere else, just to make it a little bit not as stressy. But I will tell you, it reflects the same situation as we are seeing here in Europe and in other places. And it's from Australia. It's AEMO, it's the Australian regulator, which is also influencing the requirements on the grid. You see here the transmission lines in Australia. And now I will do it very quickly for you, just to visualize for you what's going on. Now, you see here the red ones are the high generation areas. The blue ones are the small generation areas, which they have and see it as per today. You will see the number of plants which are connecting there. So still a big amount of power plants are in the, you can say, in the central regions. Now, that's the development plan for the future, for renewable wind farms and solar plants. This is a multiple value of megawatts than you can see in centralized generation. And of course, that will influence. So what AEMO did, they made a simulation. How is that influencing us? And they said, well, 2019, we have already today, when we have red spots, we have problems with inertia and short-circuit power contribution. And as we will get more renewables connected in the remote grids, in the remote areas, how will this influencing us? This is 2028. This is 2038. So this means in reality, this change from centralized power generation to decentralized power generation will influence the grid stability. What do that mean? We have done a study within corporate research within ABB, where we said if we want to transfer power from one grid to another, then when you make a study, you speak about equivalent size to make it more simple, to make a kind of simulation so that you also simulate transient behavior. And then we said, well, we have a kinetic energy, rotational energy, which the equivalent of that, the highest value which we can get out for that is if in reality not one unit is there in one generation unit, because this will not help. You will still, based on the multiplication of these two factors from the two units, you need in both areas a strong grid. It's the same for short-circuit power. If you're an electrical engineer, you very quickly will see this formula. This is the way how you calculate short-circuit power from one point to another. And it's exactly that what we need. We need the remote installation of inertia and short-circuit power contribution in the remote areas so that we are secure and operating our grids also in future. So decentralized power generation requires decentralized system support for inertia and short-circuit power contribution. For voltage control, this is already decentralized. We already do that. But this will also be required for this other type of ancillary services I speak about. Now, just a few pictures. These are installations from Australia, where the Australian regulator said, well, dear wind developer, dear solar developer, dear IPP developer, if you have non-synchronous generation, you must bring inertia, you must bring short-circuit power contribution, otherwise don't bother, don't come. We need that. So that means in reality that they have to bring also type of rotating machines together with their wind or solar or hybrids or with energy storage parks to provide short-circuit power and inertia to those grids where they want to connect. In reality, this is also an advantage for them. It makes it easier for transport. The wind farm could use the synchronous condenser also for their internal balance of plant for reactive power, which means that they could take out more active power from their inverters. Otherwise, they have to use the inverter to handle reactive power, and with this degrade a little bit their inverter capacity on the active power, which they get paid for. Now, this is another installation. This is in our workshop where we do the FAT test, this final acceptance test of the machine. This condenser will be then connected via transformer to the transmission grid. And this is how it looks when it's at site. You have the big blue box, which is the condenser, and then we have this auxiliary equipment beside, which we also deliver. It's the cooling system, the loop oil system, the pony motor, and the control and protection panels with that. This is a solution with high inertia, where we add, in the middle you see another big blue box, and that's our flywheel, where we can provide inertia of about, let's say, a half gigawatt seconds on inertia on a relatively small machine, which is quite impressive. This means an H factor of more than 6 in reality. And that is also the way why we would like to use this type of smaller units, of smaller synchronous condensers, with a lower MVR rating, with a higher inertia in those areas where we need the support. Because we don't need these big machines in those remote areas. Because normally a condenser is working with very, very low MVR values based on the fact that you don't need the MVR so much. So that means that the losses would be too high if you install a big unit. That's the reason why we say that smaller units or multiple units, it's better than big animals. This is a little bit a presentation where we did this combination of our condenser, a 70 MVR unit with a STATCOM solution of plus minus 70. Now, in this case, this was done from our power grid system group, but in reality, instead of the STATCOM, you could use a wind farm, or a solar farm, or an HVDC link, or an energy storage system to provide the quick MVRs. And then still you have both solutions, inertia, short circuit power contribution, phase angle stability, as well as the voltage regulation which you need, the quick voltage regulation which you need. Sometimes. This is a picture from our multiple units when we are working for big inertia issues, for example, for the Baltic countries or for areas where you have a decommissioning of our nuclear power plants, where we also would like to add up a number of units. In reality, this would be a good way if you have the possibility to measure your inertia. Maybe you don't need a big animal the whole time. You may switch in the modular system when the inertia is required, and not just because you have only the big unit. So a combination of modular systems with a measurement of inertia, continuously measurement of inertia, which is today offered on the market, would be a nice combination, because then you can really optimize your assets. So to come back and finalize, what is synchronous condensers doing? Well, we are an insurance company. We provide you with short circuit power, which is needed for power quality damping. We are providing you with inertia for frequency support. We are providing you with MVRs, if you would like so, for voltage control. And we are providing you with phase angle stability, which you need for all your converters. Thank you very much.
Thank you very much, Christian. Are there here any electrical engineers with some questions? Yes.
Yeah.
Hello. I'm an electrical engineer, but also a business developer. I would like to know the prices. When you compare the same function with the same provision for voltage regulation, provision of inertia, compare you the battery as the power electronics with the condenser. What is the deviation on price? What is the difference?
I can tell you, if you add a flywheel to a condenser, the price for a flywheel and the condenser will be much lower than for a battery system. You can get a condenser connected on 11 kV, let's say for €4 million. We can make the deal now. And then you will still have an inertia of about 100 megawatt seconds. If you add €500,000, you will get an inertia of about 450 megawatt seconds. And for that, you will not get much battery.
Yes, and if I may, adding to that discussion, I mean, a battery makes sense when you have various values to stack. So I think it's always a decision per project, like what is really needed in that application, in that use case, and what can the battery offer to you also other than inertia. So I think that's the discussion.
I think she's completely right. I think we need also something which is called fast frequency response. There is, the Irish grid did a very clever thing. They divided that in an inertia, which is unfortunately not very defined in time frame, which they call synchronous inertia response. And then they have fast frequency response, which is coming afterwards. So you need the synchronous inertia response to capture up to help you in reduce the rock-off, the rate of change of frequency, and to help you in the nadir, so that you avoid to come down in frequency too low. And then you need a fast frequency response to push up again the frequency, as well as the primary frequency control and secondary frequency control. It's a combination. So the important thing is that we have to build these building blocks together. Synchronous alone is not the solution, as well as not battery either.